Number 13, how many electrons a single orbital can hold? Well, that's been the basis for these two equations. Each individual orbital itself, each little room that isn't really a room, holds 2 electrons. Number 14, what the Aufbau principle states. Okay, there are 3 key names that you need to know in this part of the chapter. The Aufbau principle is number 1. Electrons want to be close to the nucleus. Electrons are attracted to the nucleus because it's got all those positively charged protons. Electrons, since they're negative, want to get near there. They will fill the lowest energy levels first. That's the Aufbau principle. Aufbau. It is from the German word that means to build on or on build. Aufbau principle. And you do need to know this by name. Okay? Electrons fill the lowest energy level first. It's coming up in the next 2 hints, state how Hund's rule affects the order of fill for electrons and what the Pauli exclusion principle states. So let me just cover all 3 of those at once. Hund's rule is the one where we were discussing how to do orbital notation with the arrows for various elements and why you had to put 1 electron in each available orbital first. Electrons are negatively charged. They would rather repel. If there are 3 orbitals available, like these 3p orbitals, and we only have 3 electrons coming along, they're each going to want to go into their own orbital. They'd like to have that space. They don't want to have to double up until more electrons come along that would fill up those orbitals. Okay? We use several somewhat colorful analogies in class for that. Think about if you had to share bunk beds. If you had to share a bed, would you rather have your own bed and throw your stuff on the upper bunk, or would you rather double up? If you can have your own space, you'd rather have your own space. That's what the electrons want to do as well. And Hund's rule, if you go back to our orbital notation, 1s, 2s, 2p with 3 orbitals, we fill our 2 electrons close to the nucleus first for an atom that has enough electrons. Then we fill up our 2s sublevel. But when it comes to the 2p, we're not going to put 2 arrows right away in one. Those electrons are going to go into their own individual orbitals before they double up. That's Hund's rule. And then the Pauli exclusion principle talks about the actual set of quantum numbers for any given electron. And the quantum numbers are like an address for an electron, or like a combination. Like all the locker comms in the building have used the same set of numbers on their dial, but any given locker would have a different comm than any other locker in the building. Any given electron around the nucleus of the atom as it goes into the electron cloud is going to have its own kind of location. Remember, they aren't fixed in that spot. They move around crazy, but we know that an electron is going to hang out there. And the Pauli exclusion principle tells us that no 2 electrons in an atom can have the same set of all 4 quantum numbers. Okay? At least one of the 4 quantum numbers needs to be different. So you could have quantum numbers like, well, 4, 0, 0, 1/2. That's an electron in the 4th energy level, s orbital, lines up around the XYZ axis, and has a clockwise spin. Okay? That element is potassium. The element next to it, calcium, has the set of quantum numbers 4, 0, 0, -1/2. Now, even though they're in the same energy level, even though they're both in an s orbital, even though they both line up the same way around the nucleus, they have to be spinning in a different direction. Okay? At least one of those 4 quantum numbers has to be different. That's the Pauli exclusion principle. Another way to look at it, you could have another electron that is 3, 0, 0, +1/2. Okay? That would be the electron in the 3s1 spot. And it could be the middle two quantum numbers as well, but you can't have two electrons with all four quantum numbers the same. Just like we don't have two lockers in this building with all the numbers on the comm that you dial up exactly the same. Number 17, the order of fill for orbitals from 1s through 6d. Now, if you can write an electron configuration for any element on the periodic table, and you should be really good at it by the time you're done with this chapter, then you know the order. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Where am I getting that? I'm just reading the periodic table on the back wall, left to right, top to bottom. Energy level 1, s orbital. Energy level 2, s orbital. Energy level 2, p orbital. 3s, 3p. 4s, 3d, because of orbital overlap, 4p. 5s, 4d, again, orbital overlap, 5p. 6s, zoom down here to 4f, orbital overlap happens twice there. As the electrons get further from the nucleus, energy levels are closer together, there's a lot more chance for overlap. So 6s, 4f, 5d, 6p. Whoops, sorry, I was down the road. 6s, 4f, 5d, 6p. 7s, 5f, 6d, 7p. Okay? Pretty easy. Left, right, top, bottom. You know the pattern. Number 18, how to write electron configurations for a specific element. So I'm going to give you the atomic number. Let's say titanium, atomic number 22. And you'll have to write the correct configuration for that. Or another way I could ask it is, what's the configuration of the highest energy level? The highest energy level electrons for an element like titanium. Well, if you can write the whole configuration for something like titanium, then this should be a piece of cake. Titanium is element number 22. Okay? Titanium. And I'm going to write out the whole thing, even though you know the noble gas shortcut. We'll do both ways. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Okay. If we wrote that with the noble gas convention, I would put the noble gas that came right before the row titanium's in. So that would be argon that ends row 3. And then I'd write the new stuff. So I'm saying I'm going to put all this stuff in brackets. Say blah, 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 argon. That means argon. Argon, 4s2, 3d2. Okay? The highest energy level orbitals for titanium would be the 4s and the 3d. You might see answer choices that just show you that part, assuming that you know that you have to follow the alphabet principle and write out the whole thing. Okay? Let's jump ahead to electron dot notation for this, because this is one where people tend to miss, especially when it comes to D block. We typically write electron dot notation for just atoms in the S or P block, but the D block elements have valence electrons as well, and in fact, sometimes the D electrons can get involved in that whole process. You need to look at this configuration and say, okay, what is the highest energy level represented? Not the highest energy orbital, the highest energy level. You look for the principal quantum number. We have choice of energy level 4 or energy level 3. And even though this 4s orbital itself snuck in and filled before the third energy level was done, technically, overall, energy level 4 is a higher energy level. So how many electrons does titanium have in that fourth energy level? it has two. We would write titanium, and I like to put my S electrons together in a pair on that side, but you know from watching the videos that there's a couple different ways to do that, and I will accept either one. Fourth energy level, 2 electrons, that's what we're going to get for the dots. You will see as we go on in chapters that the D block elements have lots of options sometimes. They have different numbers of valence electrons depending on what they're bonding with and how they're reacting. And sometimes they bring in